Alrighty, folks.
Well, I now have some. What are their top live posted profile pic?
Okay, folks. So, yesterday we talked about points of inflection. All right. A point of inflection is kind of like the relative extrema, but for the second derivative, right? Okay. So the second derivative, you remember again, we use the second derivative to determine concavity of a function. So where the original function changes from concave up to concave down, or concave down to concave up, we call that location in the original function a point of inflection. How do we locate points of inflection? How do we determine them? We use the second derivative, right? So if you recall yesterday, right, where the second derivative is positive, we know the original function will be concave up. Where the second derivative is negative, the original function will be concave down. Okay? So using that information, we did something like example 1. To determine the concavity, we took the second derivative of our function, set it equal to 0, also where it doesn't exist, right, to find those kind of like critical points, if you want to think about it in that sense. All right, and did our number line, analysis there to then determine that, okay, since the second derivative was positive on this interval and this interval, therefore f would be concave up on those intervals. And since the second derivative was concave down on this interval, since the second derivative was negative on this interval, the original function would be concave down on that same interval. Okay? So that's the gist of it right there. And then where we changed concavity, so where our second derivative changed from positive to negative, or where our second derivative changed from negative to positive, both of these locations are points of inflection. We don't have a special name for if we're changing from concave up to concave down, or concave down to concave up. It's not a special name. They're both just called points of inflection. Okay? So for number 3 here, we'll go ahead and just jump into that one, okay, and find the points of inflection for this. So determine the points of inflection and discuss the concavity of the graph of f of x equals x to the 5th minus 5x to the 4th plus x. So that means we need to do what here? Find the second derivative. So to find the second derivative, we're going to find the first derivative first, okay, so 5x to the 4th minus 20x to the 3rd plus 1. Okay, yeah, don't forget the derivative of x is 1, okay? All right, and then the second derivative. It would be 20x to the 3rd minus 60x to the 2nd plus 0, right? Because the derivative of 1 is 0. All right, we'll set this equal to 0. And then I'm going to go ahead and factor some stuff out here. I can factor out a 20x squared, it looks like. So I'll be left with x minus 3. Okay, and so we get that 20x squared equals 0, so x is 0, and we get x minus 3 is 0, so x is 3. Okay, then we can do our little number line thing here. Okay, I'm going to call this f prime prime, so we know that we're evaluating it back in f prime prime. Okay, we use f prime prime, we evaluate an f prime prime, because it is f prime prime's sign, sign, that then determines whether f is concave up or concave down, right? This is different like when we do like absolute extrema, right? When we do absolute extrema, we're evaluating those critical points back in the original function. We're using the original function in that case. So it's, this is a matter of, making sure that we're plugging things back into the right place too. And I think you guys already have a handle on, that challenge, I guess, because I've, gotten several questions in the past. Well, okay, and where do I plug this one? Where do I plug this into? So try and always think about what you're trying to find, why you're trying to find it, and that can help direct you about where you're going to plug things in too. So anyway, there's our 2 kind of like critical points or whatever, possible points of inflection, and we'll check some numbers in the interval here. So we'll try -1. This first part here is always going to be positive, right? We're going to square our number and multiply by positive 20, so it's always going to be positive. So really, it's just the x minus 3. It's going to determine our sign here. And so -1 minus 3 is negative, so it's going to be negative for that interval. And then from 0 to 3, well, 1 is in that interval, so we plug in 1. Again, still negative. And then we go to 3. After 3, so like 4. Again, 4 minus 3 is going to be positive, so overall positive. Okay. So again, the emphasis here, right, is that they don't always alternate, right? Concavity does not always alternate, so please don't assume that it does. You need to check every interval. Do not just, alternate them, okay? You need to check every interval. All right, so we can say now f is concave down, like a frown, from -infinity to 3, and f is concave up, like a cup, from 3 to infinity. Okay? And do we have any points of inflection according to this analysis? F has a point of inflection at 3. Because and again, if we wanted to justify here, we would say because f prime prime changes from negative to positive at this point. Okay, that would be your justification. Because, and I'm going to go ahead and write it here just because it's notes. Because f prime prime changes from negative to positive at this point. We were not told to justify, so we don't have to, but I'm going to put it in here just so you know. Okay. That is sufficient, but if you wanted to go, one more step to be even more thorough, you would say because f prime prime changes from negative to positive at this point, you would then say this indicates then that f changes from concave down to concave up at this location too. So yeah,
so
if you wanted
to. Is this like finding relative extrema, but it's like a first derivative?
It's kind of like, yes, it's kind of like comparable to that. Yep, similar kind of process, similar kind of like analysis and results, but just in a different context. The meaning is slightly different. Now we're talking about concavity as opposed to. Okay. Now, well, I won't. I'll hold off on that too. But you can also, of course, use the second derivative to talk about what's happening in the first derivative too, because the second derivative is the first derivative of the first derivative. So these intervals here would also indicate something about the first derivative, right? This would indicate that the first derivative is increasing on this interval, right? These would indicate that the first derivative is decreasing on these intervals. This would indicate that we have a relative minimum in the first derivative because the second derivative is changing from negative to positive, okay? Don't worry too much about that right now, but eventually we want to be able to analyze the first derivative using this information too, in the same way that we use the first derivative to analyze the original function. Anywho, questions on this? All right, we'll try this next one here. So the good news is find the points of inflection of f of x where x is greater than negative 1 given, and we already have the first derivative here, so that's nice, okay? Because if we had to take the second derivative of that would be messy. Okay, I'm going to rewrite this though as x times x plus 1 to the positive 1/2 power instead of leaving the square root there. It's just a little bit easier for us, right? So when we go to take that second derivative now, what rule are we going to have to use here? Product rule and also chain rule, yeah. So second times the derivative of the first, so 1, plus the first times the derivative of the second, so that's going to be 1/2 x plus 1 to the negative 1/2, and then times the derivative of what's inside, but the derivative of what's inside is just going to be a 1, so we don't have to worry about that. Okay, I kind of maybe went a little bit overboard there with the parentheses. Now, when we do a product rule, we are able to, at points, right, factor out a greatest common factor. Do we have a greatest common factor here we could factor out? We actually could. We actually could factor out a GCF here. So let me kind of speak to this in two different ways here. So this is not so much important to the calculus. This is more important just to like the algebraic simplification. And I'm just trying to offer you an alternative strategy to solving this. Okay? Because right now, if we leave it the way it is and we try and simplify this, we're going to end up with this. Let me just go ahead through it here. We'll have the square root of x plus 1. So I'll just leave it like that. Plus, and then this is going to become x over 2 times x plus 1 to the 1/2. Okay, so let me just make sure we're all okay with that. Okay. And we're just on example 4 in the notes there. Okay. So, but anyway, you can see the issue we're going to have because now we're going to want to set this fraction, this sum here equal to 0. And so, like, in order to solve this, we'll have to get like a common denominator, and it's going to get kind of messy and stuff like that. But again, let me show you an alternative here. So well, I guess I should ask, is everyone okay with the fact that this would transform to this, right? Because again, x plus 1 to the negative 1/2, it would go into the denominator with a 2. The x is really x over 1, so the x would go up in the numerator, so you'd end up with this. And it's kind of, you can imagine setting this equal to 0 and trying to solve it. It would be tricky. We'd have to get a common denominator, combine like terms, simplify, and then, go from there. But let me give you an alternative here. If you look here, right, we do have an x plus 1 common factor. And so we can actually say this is equal to, now, I'm going to factor out an x plus 1 here. But I should factor out the x plus 1. What power of x plus 1 should we factor out here? Negative 1/2. And the reason for that, okay, if you think about when you normally factor x, I'll do this in the paper so that way people that watch, if they do watch, will be able to be helped out by this. If you think about your normal GCF factoring, like if I want to take x cubed plus x squared and I want to factor the GCF out here, what is the GCF I can factor out here? X squared, right? So we are limited by the smaller of the two powers, right? We can factor out the smaller of the two, x squared here. We can't take an x cubed out because there's not enough x's there to do that. Same kind of principle applies here. We are limited by the smaller of the two powers. So we're going to factor out an x plus 1 to the negative 1/2. Okay, which will leave behind. All right, so I'm going to ignore this first term for right now. I'll leave some space and put a plus. And let me just focus on this one, right? If we take x plus 1 to the negative 1/2 out of this, what's left over? Just a 1/2 x, right? Just a 1/2 x. So that's easy enough, right? But if I take an x plus 1 to the negative 1/2 out of this, what will be left? X plus 1 to the actually positive 1 here. Here's why. Here's why, okay? So when we use that phrase taking out, what mathematical operation are we actually doing? When we factor something, what mathematical operation are we doing? We're dividing out. We're dividing out, right? If I take an x squared out of this, I'm really dividing out an x squared from each term, right? Factoring it out is dividing. When I take x plus 1 to the positive 1/2 and divide it by an x plus 1 to the negative 1/2, so again, I'm going to write it over here. And I divide out an x plus 1 to the negative 1/2. How do we simplify exponents when we are dividing? What do you do with your exponents? And you have the same base. What do you do with your exponents? Subtract. So 1/2 take away negative 1/2, positive 1, right? 1/2 take away negative 1/2 is positive 1. So you're left with x plus 1 to the 1. All right, which then, if we simplify this, becomes x plus 1 to the negative 1/2 here. X plus 1 plus 1/2 x leaves us then with 3/2 x plus 1 there. And now I can rewrite this as 3 over 2x plus 1 all over x plus 1 to the 1/2. Okay? Oops. Let's scoot that out there. Okay. This is the similar, you would expect a similar result here in this problem too. Okay? You'd expect a similar result here in this problem, but this is what we get going this way. Okay? So it saves some time, but it requires a little bit more, complex calculation, I guess, or whatever. But it will get easier with time when you try this. Okay, it will get easier with time. Your choice how you decide to pursue this problem, though. If you want to go this way, again, you'll have to get a common denominator and combine like terms. Here, the common denominator is kind of taken care of by that GCF that we factored out. Okay, we result in that. Okay, so either way, we now have the second derivative and it's simplified. What do we do now? Set it equal to 0. Okay. Or undefined, right. Now, so we'll set the 3/2 x plus 1 equal to 0. Oops, I'm going to do it over here. So I'll subtract 1 from both sides. 3/2 x equals negative 1. And then multiply both sides by 2/3. So x equals negative 2/3. Okay. And then I'll set the denominator equal to 0. X plus 1, excuse me, to the 1/2 equals 0. We'll square both sides. X plus 1 equals 0 still. And then we get x equals negative 1. Now, x equals negative 1, though, we're going to throw that out because we're only interested in x values that are greater than negative 1. So we throw that one out. Okay, and just the negative 2/3. Negative 2/3, right, is greater than negative 1. Okay, right, it's a little bit less negative than negative 1 is. Okay, so negative 2/3 is our only, kind of value there. So I'm going to kind of like make my number line. I'm going to start my number line at negative 1 since we're only considering x values greater than negative 1. And I'll write negative 2/3 in here too. Okay. And so then we'll pick a value here and plug it into our second derivative to evaluate here for the points of inflection. Okay. So we need a number between negative 1 and negative 2/3. Say what? Negative 1/2? That wouldn't quite be there. Negative 3/4, we could use that one. Okay. So negative 3/4 times 3/2 Okay, so let me do this here. 3 halves times negative 3/4 plus 1. So that's going to give us negative 9/8. And negative 9/8 plus 1 is going to be negative, right? And then we're going to do negative 3/4 over now, I guess. Negative 3/4 plus 1 to the 1/2. But negative 3/4 plus 1, positive, right? Negative 3/4 plus 1 is positive 1/4. Square root of that will still be positive, positive 1/2. And so we have a negative divided by a positive, so negative overall. Okay, that one's a bit tricky with the fractions and stuff in there. Let's pick 0 in this other interval, though. Much easier, right? 0. So 0 times 3 halves is 0, plus 1 is 1. 0 plus 1 is 1. Square root of that is still 1. So we get a positive for that interval. Okay, so F is concave up from negative 1, negative 2/3 to infinity. F is concave down from negative 1 to negative 2/3. And so do we have a point of inflection here? Yes, we have a point of inflection where? At negative 2/3. Yeah. Point of inflection for F at x equals negative 2/3. Huzzah. Okay? Questions on any of that? Yes, Steve.
So in order for there to be like a point of inflection, it has to go from negative to positive or positive to negative?
Correct. The second derivative must change from negative to positive or positive to negative, which would indicate that the function is changing from concave up to concave down or concave down to concave up. Yes?
The question only says find the points of inflection, so but like if we see a question like that, we know we have to find the concave up and concave down.
Right. Exactly.
So we have to say, okay.
I mean, do you need to say this? No. Okay, so you're right. I did kind of do overkill there. You wouldn't need to write the concave up, concave down part. You can just say point of inflection for F if you want. That's all. That's sufficient. Of course, if it says then justify, you'll want to say because, F prime prime is changing from negative to positive or positive to negative, whatever is the case at that point. Okay? Yes, thank you for pointing that out too. All right, so we're going to now finish up here by talking about the second derivative test. Okay? The second derivative test, if you remember, we had the first derivative test. What did the first derivative test allow us to find? The focus of the first derivative test, if we go back, was to find relative extrema, actually. Okay? The focus of that first derivative test was really for finding relative extrema. Yes, we used the fact that, F is changing from increasing to decreasing and stuff like that, but the first derivative test is really used to find relative extrema. Okay? How did we find those relative extrema? Using the first derivative. That's why it's called the first derivative test. It's using the first derivative to determine relative extrema. Well, now introducing the second derivative test, which is also used to find relative extrema of the original function, but instead of using the first derivative to determine the relative extrema, we're going to use the second derivative to determine the relative extrema. Now, let's think about this. If we're going to be using the second derivative, what does the second derivative tell us about the original function, behavior-wise? If the function is concave up or concave down, right? So we want to use concavity here to somehow determine whether our original function has a relative maximum or relative minimum. What type of concavity exists at a relative maximum but not at a relative minimum?
Concave down.
Concave down, exactly right, right? At a relative maximum, it's going to look like this, right? There's a relative maximum right there, but isn't this behavior concave down throughout? Right? Whereas, compare that to a relative minimum, what kind of concavity do we expect at a relative minimum? Concave up, like a cup, right? Because there would be our relative minimum, and so we would expect concave up behavior around there. Okay? And so this is the essence of the second derivative test. So let f be a function such that f prime of c equals 0. So you still have to use the first derivative to get your critical points. So you kind of might be wondering, Mr. Wood, then why do we even bother using the second derivative test if we already have to use the first derivative? Well, you'll see we can set up problems in such a way that you'll know the critical points, but you won't be able to necessarily find the first derivative and actually do the analysis normally. So we can make it, we can write problems in such a way that you have to use the second derivative test and you can't use the first derivative test. Okay? Anyway. So let f be a function such that f prime of c equals 0, and the second derivative of f exists on an interval containing c. Okay, if f prime prime of c is greater than 0, indicating what kind of concavity? Concave up, then f of c is a relative minimum. Of f. If f prime prime of c is less than 0, what kind of concavity is that? Concave down, then f of c is a relative maximum. Ooh, but if f prime prime of c is equal to 0, the test fails. Okay, so the second derivative test, interestingly, fails if the second derivative equals 0, right? We can't determine the concavity at that point, or the concavity, sorry, is 0, okay? It's not concave up or concave down, and so we have to then go to the first derivative test, or at least say inconclusive, okay? At least say inconclusive if we maybe can't use the first derivative test. All right, so let's do it here, okay? So find the relative extrema using the second derivative test. So in order to use the second derivative test, we're going to get the second derivative. Okay, so I'm going to do that by first getting the first derivative. So negative 12t to the third plus 12t. Okay. Before I go and take the second derivative here, I'm going to go ahead and come up with the critical points. We still need to have those critical points. So I'll set the derivative equal to 0. Okay. So I'm going to go ahead and factor out a 12t here as well. So we're left with a negative t squared plus 1. Okay, so you get t equals 0 and negative t squared equals negative 1, or t squared equals 1, or t equals plus or minus 1. Okay, so those are our three critical points. All right, but we're not going to do our number line analysis with this, even though we could. We're going to use a second derivative test, so I'm going to go to the second derivative now. Negative 36t squared plus 12. Negative 36t squared plus 12. All right. And so then how do we use our second derivative? Well, we're just going to take these critical points and evaluate the critical points. So f prime prime of 0, at 0, what's the concavity? That's what we want to know. At 0, what's the concavity? So we plug in 0, 0 squared, 0 times negative 36, still 0, 12. So at 0, in the original function, what is the concavity of the original function? Concave up, right? We have f prime prime of 0 is a positive 12, so f is concave up. Therefore, relative minimum of f at 0. Okay, that's the second derivative test. That's how we use it. Okay, we'll do the same thing. We'll plug in a positive 1. F prime prime of 1. 1 squared, 1 times negative 36. Negative 36 plus 12 is going to be negative, right? Negative 24. So what kind of concavity do we have at x value 1 in our original function? Concave down. So therefore, we have a relative okay. And if you plug in negative 1, well, you're going to square the negative 1 anyway. One sec, Clayton, I'll be right with you. Negative 1 squared is going to be positive 1 times negative 36 plus 12 will still be negative 24. And so we again get the same thing here as well, but for at x equals negative 1 as well. Okay? So two relative maximums at 1 and negative 1, and then one relative minimum at x equals 0.
How do you know which points to test? Like you chose 0 and 1.
Where did I get those numbers from?
Yeah. From the first.
Exactly. So it's the critical points. You still have to find the critical points, setting the derivative, first derivative equal to 0.
You put them in that prime.
Put those back in the second derivative.
And then that, if it's positive or negative, it'll tell you if it's a minimum or max.
Mm-hmm.
Okay.
Mm-hmm. Exactly right. All right, so let's look at number 6, and then we will get you guys, we'll be done, okay? So for all x in the closed interval from 2 to 5, the function f has a positive first derivative and a negative second derivative. Which of the following could be the table of values for f? Okay, so the function f has a positive first derivative, means the function should be what? Increasing. Can we eliminate any options here based on the fact that we know alone f should be increasing? The last one and the next to last one, right? Both of those can be eliminated. All these other ones, they are increasing. Okay? Now, negative, whoops, I almost gave it away, right? So if you have a negative second derivative, that means we are going to be concave what? So increasing concave down, let's think about what it's going to look like. Increasing means I need to go up from left to right, but concave down means I need to kind of like be more frown-like. So it's going to look like that, right? That's increasing concave down. So I need to be increasing, but how am I increasing? What's that, Carter? Yeah, decreasingly increasing, if that makes sense, right? We are increasing still, but we're increasing by a less and less amount each time, right? So that second derivative being negative means we're concave down, so we are decreasingly increasing. All right? So which one of these tables indicates us decreasingly increasing? The third one, so let's see here. So 7 goes to 11, so that's plus 4. Then we go up plus 3, then we go up plus 2. Yes, it's going to be this third one. If you look at this one right here, we're going up 2, 2, 2. That is a constant increase, right? And here we're going up 2, then 3, then 4. So that's increasingly increasing. That will be increasing concave up. Okay, so it's going to be this one. All right? And that's all I have to say about that. All right? So we won't be getting to this until Tuesday. All right, so Monday will be a work day, and then Tuesday we're going to be getting into that next section there. Okay, so now you have all the things you need for the test or for the homework. That I gave you last night. There is no additional homework tonight, so you have the remainder of class time to work on that homework. Okay, or just kind of take a break if you would prefer.
Sir would.
Yeah, there is no additional homework. There's the same homework from last night.